Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to be going over real life stoichiometry problems. So we're going to take stoichiometry and we're going to apply it to real life situations. So let's get into this. So the first problem has to do with airbags. So here is the chemical equation or the reaction that occurs in airbags to inflate your airbags. And so the problem that we are going to deal with is whether or not you have enough of your reactants to create enough of the nitrogen gas to inflate your airbag all the way. So let's get into this. So here it says if an airbag is made with 90 grams of NaN3, will it be safe? So safe meaning will it inflate all the way? So we're going to assume that 65.1 liters of N2 gas are needed to inflate an airbag to the proper size to protect you in an accident. So one of the pieces of information we're going to be needing is the density of nitrogen gas at this temperature, whatever this temperature is. And that is 0.916 grams per liter. So that's the density of nitrogen gas. So we can use that as a conversion factor in our problem because this is relating grams, mass in grams of your nitrogen gas to liters of volume in your nitrogen gas. So, and we want to have 65.1 liters. So we have our roadmap here. And so the first thing we want to do is pull out all of the conversion factors in our problem. Anything that is a relationship to something else. And as I pointed out, this here is a relationship where we have grams of nitrogen gas equal to liters of nitrogen gas. So we can use that. So we'll put that up here. So we have let me erase this. So here we have 0.916 grams. So 0.916 grams of N2 gas is going to be equal to 1 liter of N2 gas. So we're going to be able to use that as a conversion factor. So that's the only thing that they've given us. So as far as conversion factors go, the other conversion factors we'll get to in a moment. So the next thing we want to do is pull out where are we beginning in the problem and where are we ending? And as I always say, the end of the problem is the beginning of the question. So what is the question? It says, if an airbag is made with 90 grams of NaN3, will it be safe? So that's the question, meaning, will it be safe? Meaning, will we be able to have 65.1 liters of nitrogen gas formed? So, but they're giving us 90 grams of NaN3. So we want to know how much nitrogen gas is produced. Will it be safe? Will we produce the 65.1 liters or not? So the question is, how much will be produced of the nitrogen gas? So we want to know the liters of nitrogen gas. How many liters of nitrogen gas? And where do we begin? Well, the only other piece of information they gave us is 90 grams of NaN3. So that's where we need to begin. So we're going to begin with 90 grams of NaN3. All right, so now we know where we're beginning. We know where we need to go. And so in between, all we're going to do is use conversion factors to convert this to this. So as always, we begin with what we're given. So we begin with 90 grams of NaN3. And we put it over 1. And so now we want to use a conversion factor. So here is our roadmap. So notice that we have our roadmap here. So as I said before, the roadmap tells you where what to do to go from where you start to where you end. Now notice that we're starting with grams of our NaN3. So we're starting with grams of A. So grams of A, but we want to get liters of nitrogen. But notice there's no liters in here. But we do have a relationship between grams and liters. So we're going to convert to grams of B, our nitrogen gas. And so therefore, we're going to have to make another conversion here. So we're kind of going off of the main road, off of the highway. So we're going to need an extra step here to go between grams and liters. So we want volume of B, right? And that's going to be in liters. And we have the density. So this is where we're going to use density to make that conversion. So that's an extra step off of the main highway. So this, we're going to start here and we're going to end there. So these are the steps we need to go through. So the first step is we need to convert mass in grams to moles using the molar mass of A, MMA, molar mass of A. So what's the molar mass of sodium azide? So NaN3. So we calculate that up. We add up the atomic masses of all of the atoms, and we get 60. What do I have? 65.01 grams of NaN3, and that's going to be equal to 1 mole of NaN3. So this is our first conversion factor, this relationship here. So since I have grams of NaN3 on the top here, I want grams on the bottom. So I have here 65.1 grams. So I'm going to put 65.01 grams of NaN3. And then on the top is going to be the moles, 1 mole of NaN3. So 1 mole of NaN3. So grams cancels out, and now I have moles. So now I'm here, moles of A. So what's my next step? I got to go from moles of A to moles of B using the mole ratio between A and B. Where am I going to get that? From the balanced chemical equation. So the mole ratio between NaN3 and B is what? N2. So it's a 2 to 3 ratio. 2 moles of NaN3 is going to give me 3 moles of N2. So let's go ahead and use that mole ratio. So since I have moles of NaN3 on top here, I want moles of NaN3 down here to cancel out. So 2 moles of NaN3, 2 moles of NaN3, and on top is going to be 3 moles of N2, 3 moles of N2. So moles of NaN3 cancel out. Now I have moles of B, which is moles of N2. So now I am here on my roadmap. I've got 2 more steps. So now what's the next step? Moles of B, the mass of B in grams. I'm going to use the molar mass of B. So I'm going to use the molar mass of N2. And so there, as we said before, the molar mass is going to be 28 grams, 28.02 grams of N2 is equal to 1 mole of N2. So now I have this relationship here that I can use as a conversion factor. So I have moles of N2 on top here. So I want moles of N2 on the bottom. So 1 mole of N2 goes here. 1 mole of N2. And now I have 28.02 grams is going to go on top. So 28.02 grams of N2 is on top. Moles of N2 cancel out. And now I have mass of N2, which is B. My last step, I'm going to go from grams of B to liters of B using the density. So this is where this comes in here. So my last step, since I have grams of nitrogen on top, I want grams of nitrogen on the bottom. 0.916 grams of nitrogen is here. So I'm going to take the 0.916 grams of N2, and that's equal to 1 liter of N2. So 1 liter of N2 goes on top. So grams of N2 cancel out. Now I have liters of N2 on the top. Liters of N2 is what I'm looking for. I am done. No more conversion factors. I've reached my destination on my roadmap. So now all I need to do is take my calculator and multiply everything on the top. So 90 times 1 times 3 times 28.02 times 1, and then divide everything on the bottom. Divided by 1, divided by 65.01, divided by 2, divided by 1, divided by 0.916. So I'm doing it all on my computer, on my calculator. And so again, you don't really need to multiply and divide by 1, but I'm saying that in case, just to show that whatever's on the bottom, you're dividing by. Okay, whatever's on top, you're multiplying by. And so when you do that, you get the answer as follows. And that is 63. So the answer is 63.52 liters of N2. So that is the amount of N2 gas produced from 90 grams of NaN3. But for safety, we want 55.1 liters. We don't have enough. So that means that 90 grams is not enough to produce a safe amount of N2 to inflate your bag all the way. So this would not be safe. So that's my first example. Let's go on to the second example. Okay, so our next real life stoichiometry problem has to do with rocket fuel. So in this problem, we're asked if the Saturn V rocket was loaded with 770,886 liters of kerosene fuel and 890,650 liters of liquid oxygen, would it have enough liquid oxygen on board to use up all of the kerosene in order to get out of the atmosphere? Okay, so that's our problem. Two things that we should know is the density of kerosene. So we're given the density of kerosene is 749 grams per liter, and the density of liquid oxygen is 1141 grams per liter. So what do we need to do? Well, we need to figure out what our conversion factors are that they gave us in the problem. So first, they gave us the densities of kerosene and liquid nitrogen. So those are going to be useful. We also have here the density of water. Not that I don't think we're going to be using this, but this is a density you should know, right? So the density of water is 1.0 grams per 1 milliliter of water. So 1 to 1 is the conversion factor. And again, that's at a particular temperature. I think it's 25 degrees Celsius, but generally you want to know that that's the density of water. So the density of kerosene they gave us is 749 grams. So 749 grams of, I'll just say kero for kerosene. is equal to 1 liter of kerosene. Okay, so what else? They gave us the density of liquid oxygen. So the liquid oxygen is 1141. So 1141 grams of liquid oxygen is equal to 1 liter of liquid oxygen. Not Q, should be O. So oxygen. Okay, so the next thing is, where do we begin and where do we end? And again, the beginning of the question is the end of the problem. So where's our question? The question is, would it have enough liquid oxygen? So we wanted to know how much liquid oxygen does it have? So would it have enough liquid oxygen on board to use up all of the kerosene? So we know how much liquid oxygen they gave us. So we have 890,650 liters. Is that enough to react with all of the kerosene? So what we need to do in this case is start with the liters of liquid oxygen they gave us and convert that to the amount of kerosene it would react with. And then we can compare that with the kerosene they gave us. If this is converted to an amount of kerosene that is less than this, then we don't have enough kerosene to react to with the liquid nitrogen. If we have a number, so let me restate that. So if we use our liters of liquid oxygen and convert that to liters of liters of oxygen and convert that to liters of kerosene, if the amount of kerosene we need to react with this is greater than what we have, if the number we get from this number is larger than this one, then this is not enough. Right. But if the number of liters of kerosene we get is less than this number, then we have enough. So let's go ahead and calculate the liters of kerosene. So we want to start with the liters of oxygen. I'll write this down here. So we want to find the liters of kerosene from the given liters of liquid oxygen. So from 890,650 liters of liquid oxygen, we want to know how many liters of kerosene that's going to produce. Now, so here's our roadmap. So we will start from mass of A to moles of A and go from moles of A to moles of B and moles of B to mass of B. But we're not starting with mass, we're starting with liters. So we got to do some conversions before we get onto the main highway. So we want to get to grams of A. Our A in this case is liquid oxygen. So how do we go from liters of liquid oxygen to grams? That's where the density is going to come in. So we can use this as a conversion factor. So we're going to start with what we're given. So we're given 890,650 liters of liquid oxygen. We're going to put that over 1. And our first conversion. So just to add this to our main highway. So we want to go from liters or volume, right? Volume. So we want volume of A in liters. So volume of A in liters to mass, and we're going to use density. So we're going to use the density there. And then when we get here, we're going to use density again to get to liters of kerosene. So again, we're going to have to add to our roadmap here. So from grams to liters, we want volume in liters of B here. And again, we're going to use density there. So we have to use density to get on our main road. And then when we're on the main highway, we're going to use this road map here, and then we're going to take a detour off of the main highway here. So, so we're at liters. We want to get to mass in grams, so we're going to use the density of liquid oxygen. So here we have liters on the top here, so we want liters on the bottom. So we're going to put 1 liter of oxygen on the bottom. So 1 liter of liquid oxygen on the bottom and 1141 grams on the top. So 1141 grams of oxygen on the top. So liters cancels out. So now we've done our first step. So we've gone from liters to mass. Now we're on the main highway. So mass in grams to moles using the molar mass of A, which is oxygen. So we're going to use molar mass as a conversion factor. So the molar mass of oxygen is 32 grams. So that means that 1 mole of O2 is equal to 32.00 grams of O2. So since we have grams of O2 on the top, we're going to put grams on the bottom to cancel out. So that's going to be 32.00 grams of O2 on the top here. So, and then 1 mole is going to be on the top. So 1 mole of O2 is here. So grams of oxygen cancel out. Now I have moles. So here I am now on this part, the leg of our trip. So now I'm at moles. Now I want to go from moles of A to moles of B. And again, we're going to use the mole ratio between A and B. And we're going to use that, get that from our balanced equation up here. So since I'm converting from moles of oxygen to moles of kerosene, I want to get to kerosene. So I'm going to go from here to here, right? So 2 moles of kerosene reacts with 37 moles of oxygen. So I'm going to do another conversion factor. So I have moles of oxygen here. So I want moles of oxygen on the bottom. So that's going to be 37 moles of oxygen. So 37 moles of oxygen on the bottom here. And then on top, I'm going to have moles of kerosene. So 2 moles of kerosene. So 2 moles. And I'm just going to put kero for kerosene rather than the formula. And so the moles of oxygen cancel out. And now I have moles of kerosene. And so now I'm at moles of B. So I've got 2 more steps. So I got to convert moles to grams. I'm going to use the molar mass of B. And so I'm going to do that. And so then I got to calculate the moles of B. I mean, what's the molar mass of kerosene? So I calculate that out by adding up the atomic masses of the carbons and hydrogens, and I get something like 170.33 grams. So 1 mole of the kerosene is equal to 170.33 grams of the kerosene. And so since I have moles of kerosene on top here, I'm going to put moles on the bottom. So that's 1 mole. So I'm going to put 1 mole of kerosene on the bottom and 177.33 on the top. 170.33 grams of kerosene on the top. So moles of kerosene cancel out. Excellent. Okay, so now I have grams of kerosene. So now I'm going to convert that. My last step is to grams to liters. And I'm going to use the density of kerosene, which is 749 grams per liter. So finally, since I have grams on the top, I want grams on the bottom. So here we go. So 749 grams of kerosene goes on the bottom, 749 grams of kerosene, and then 1 liter of kerosene on the top, 1 liter of kerosene. So grams of kerosene cancels out. Now I have liters of kerosene on the top. That was the original what I want. So liters of kerosene is what I want. So I'm done. So now all I need to do is multiply across the top and divide by everything on the bottom, and I'll get the answer. And if we calculate that out, we get 390,374 liters of kerosene. And so what this means is this is the amount of kerosene that would react with this given amount of oxygen. So, but what is the amount of kerosene that we're given in the rocket? This is the amount of kerosene, 770,889 liters. But the amount of oxygen we have only reacts with this amount of kerosene. So we don't have enough oxygen to react completely with all of the kerosene. So therefore, the rocket will not be able to leave the atmosphere. Okay, what about the next problem? So our next real life problem, problem number 3. Okay, problem number 3. So our final problem. Hydrogen powered bicycles. So here is the formula, the equation for creating a reaction for creating hydrogen. So if you have sodium silicide solid reacting with water, you'll form this substance solid, plus you'll form hydrogen gas, which then this hydrogen gas can be used to power these bicycles. So then the question is, if you start with 1 kilogram of sodium silicide and your tank can hold 500 milliliters of water, will you have enough water in the tank to use up the battery? So this is the reaction that's happening in the battery. Okay, so we have our roadmap here, mass in grams to moles using the molar mass of A, moles of A to moles of B using the mole ratio between A and B in our balanced equation, and then moles of B, the mass of B in grams using the molar mass of B. So first thing you want to do is pull out the information that they're giving us. We want to know what we're going to be doing. So one thing you need to know is they're giving us kilograms of the sodium silicide. So we're going to need to get to grams. So we're going to need to convert that mass in kilograms to grams. So here we're going to have mass of A in kilograms, and we're going to have to use a metric conversion. And we know that 1 kilogram, if we know our prefix multipliers, we know that kilo means 1,000. So 1 kilogram is 1,000 grams. So 1 kilogram is 1,000 grams. Or you can use the King Henry died by drinking chocolate milk to convert from kilograms to grams, moving the decimal point. So those of you who know that mnemonic, you could use that. But I will use the conversion factor here. And so we also want to get to what? So we want to know we have 500 milliliters of water. Is that enough? So we'll have to convert to water. But I will continue this problem in part 2. So please stand by. If you like this video so far, please make sure you hit the like button, subscribe to my channel, hit that notification bell up there, and also comment in the comment sections. Let me know what you think. Thanks for joining me. Have a great day.